Hi, as a continuation of section 12.5, we will do vector equation and scalar equation for the plane. In part A, we covered um, vector equation, symmetric equation, and parametric equations of a line. In this part of 12.5, we are going to cover vector equation and scalar equation for a plane, and also we are going to do angle between two intersecting planes, and then we are also going to find out the distance of a point from the plane. So here, so let's consider a plane as given in blue color here. So here, R R0 is a point which is, R0 is the position vector of a point P0, which has coordinates x0, y0, z0. And P is any point on the plane with coordinates x, y, z, then OP is its position vector R. So just as the way we did a line with a direction vector, in order to write down the equation of a line, instead of a slope, instead of the word slope, we use the word direction vector. We need the direction vector. Here, to write down the equation of the plane, we need a normal vector. There are infinitely many vectors on the plane. So we are going to find out something that is unique about this plane that is provided by the normal vector. So that can be only one normal vector, and maybe there are parallel normal vectors to the scalar multiples of that, but that can be only one normal vector to this plane. That's a normal vector we are going to take to write down the equation of this plane. So P0, the vector R is OP, vector OP0 is R0. So using the triangular law, we get that the directed line segment from P0 to P is R minus R0. So the line segment, the vector P0 to P is vector P minus vector P0, which is R minus R0 vector. If I assume, we consider n to be the normal vector, n is the normal vector given in the picture in pink color, normal vector. So if there are two vectors which are each of them are perpendicular to each other, then that dot product is 0. So vector equation of a plane that passes through a point, in this case it is P0, which is x0, y0, z0, with the position vector R0 and has the normal vector n, this is orthogonal to the plane, is n dot R minus R0 equal to 0. The dot product should be 0. Or equivalently, n dot R equal to n dot R0. So if we distribute n dot R minus n dot R0, so if you take the negative to the other side, it becomes n dot R equal to n dot R0. All these are vectors here. So if we write the scalar equation of this, so this is the vector equation of, this part is the vector equation of the line, the vector equation of the plane, okay? So this is the vector equation of the plane. Now how do we write the scalar equation? The scalar equation of the plane through the point x0, y0, z0 with a normal vector n which has components a, b, c is given by, so all that we are going to do is take this vector equation, then we are going to do the dot product. So n dot r minus r0, so if you consider this line here, r minus r0 is something like x, y, z vector minus x0, y0, z0 vector. That will be x minus x0, y minus y0, z minus z0. Normal vector is given to be a, b, c, the component form. So if you do the dot product, n dot r minus r0, we will have vector a dot a comma b comma z dot product with x minus x0, y minus y0, z minus z0 equal to 0. They are orthogonal to each other. One vector is perpendicular to the other. So this will give us A times x minus x0, B times y minus y0 plus C times z minus z0 equal to 0. So that is the scalar equation of the plane. That is A times x minus x0 plus B times y minus y0 plus C times z minus z0 equal to 0. Now you consider the above scalar equation of the plane can be rearranged and be written in the form ax plus by plus cz plus d equal to 0, where d equal to negative x0 plus by0 plus cz0. This scalar equation is a linear equation in xyz. So we can actually derive this equation from what we have done here. So if you consider the scalar equation in the form a times x minus x0 plus b times y minus y0 plus c times z minus z0 equal to 0, we will have ax plus by plus zz on the left hand side. And these terms with the negative terms on the left hand side can be taken to the other side. So ax0 by0 plus cz0 you can write like this. So if you move everything to one side, you get ax plus by plus cz minus of ax0 plus by0 plus cz0 equal to 0, which can be written as ax plus by plus zz plus d equal to 0, where d is given by this negative expression, where with the negative sign here. So equation of the plane written in the scalar form is ax plus by plus cz plus d equal to 0. Either this form or this form, both are equivalent. So the scalar equation is a linear equation in xyz. So what are a, b, and c? A, B, C, the coefficients of x, y, z in the plane are the components of the normal vector to the plane. So the next paragraph summarizes what this plane is about. How do you find a vector perpendicular to the plane? If you know the equation of the plane in the form ax plus by plus cz plus d equal to 0, which is a scalar representation of a plane, which is linear equation in xyz, the coefficients of x, y, and z, they are the components of the normal vector. So the normal vector, which is a multiple of ABC, vector ABC, either vector ABC or some scalar multiple of ABC also is allowed. If an equation is not known, what we can do is we can find out 2 points on the plane, and then we can find out 2 non-parallel vectors that lie in the plane. If you know 2 non-parallel vectors lying in the plane, by using the cross product of those 2 vectors, we can find out the vector that is normal to both vector A and vector B. So that will give us the normal vector to the plane. So that is a vector cross product of these 2 vectors that are lying on the plane. Then this problem is covered in my YouTube video. Please check the YouTube video corresponding to 12.5. This problem is covered there. Same way, this problem is also covered in my YouTube video. So we saw earlier how we find out angle between two vectors by considering the cosine of theta as A dot B over length of A times length of B. That gives the angle between two vectors. Now we are finding here angle between two intersecting planes. The angle between two intersecting planes is defined as acute angle theta between their normal vectors. The angle between the two planes is angle between the two normal vectors to the plane. So if n1 is a normal vector to the first plane and n2 is a normal vector to the second plane, then cosine theta is given by vector n1 dot vector n2 divided by length of vector n1 times length of vector n2. It's exactly similar to the formula that we did for angle between two vectors. In this case, instead of any two vectors, we have to say the two normal vectors. The angle between two planes is given by cosine of theta equal to n1 vector dot n2 vector divided by length of n1 vector times length of n2 vectors, where n1 and n2 are the normal vectors. How do you tell if two vectors are parallel? Two vectors are parallel if and only if one is a scalar multiple of the other. In addition, two non-zero vectors are parallel if and only if their cross product is zero. A cross B would be zero. How do you tell if two vectors are perpendicular? The two vectors are perpendicular if their dot product is zero. How do you tell if two planes are parallel? The two planes are parallel if their normal vectors are parallel. So after this, I have shown this problem number 54 on my YouTube video. Please take a look at that. This will correspond to, also it is there in the practice exam questions. So check my YouTube video for the section 12.5. You will find problem number 54, which will say 12.5.54. And next part of this section, 12.5, is how do you find the distance from a point to the plane? So the point from the point P1 to the plane, which is passing through the point P0. So let P0 be x0, y0, z0, which is this point. And be any point in the plane. Ax plus by plus cz plus d equal to 0. The equation of the plane is given. Which is ax plus by plus cz plus d equal to 0. Once you know that, the equation is given a linear equation in x, y, z, which means that the components, the coefficients a, b, c are the components of the normal vector n. And let's join the line segment from P0 to P1. So remember, P1 is the point outside of the plane where you want to find out the distance of the plane from this point. And you're drawing P0 is the point on the plane. You're connecting P0 to P1. So when you connect the line segment P0 to P1, the vector P0 to P1 is vector P1 minus vector P0. We should always reverse the order in order to find out the line segment joining the 2 points. So P0 to P1. So first you have to write down the components of P1. So x1 minus x0, y1 minus y0, z1 minus z0 are the components of the vector B, which is the line segment joining P0 to P1. Then the distance D from the point P1, so that's a distance, that's what we are finding, from the point P1 to the plane is equal to the absolute value of the scalar projection of B onto the plane's normal vector n, which has components a, b, c. We know the components of the normal vector to be a, b, c because the equation of the plane is given in terms of a, b, and c. So the coefficients of x, y, z determine the components of the normal vector. So if you notice here, if theta is this angle shown in the picture, the scalar component, the scalar projection of B onto n is what the angle is, or what the distance d is, right? So it is the absolute value of the scalar projection of B onto n. So by the formula, we know that it is n dot b or b dot n over length of n. Everything is absolute value. So we know the vector n here. Vector n is a comma b comma c. Vector b is the vector x1 minus x0, y1 minus y0, z1 minus z0. So n dot b is a times x1 plus b times y minus y0 plus c times z minus z0, the absolute value of this, divided by length of n, which is square root of a squared plus b squared plus c squared. The numerator, if you collect only the positive terms, so it is ax plus by plus cz. If you collect all the negative terms, it's ax0 plus by0 plus cz0. Outside you have a negative sign, divided by square root of a squared plus b squared plus c squared. So this value x0, y0, z0 is a point on the plane. So that means x0, y0, z0 must satisfy this equation. So x0, y0, z0 lies on the plane ax plus by plus cz equal to 0 plus d equal to 0. So which means ax0 plus by0 plus cz0 plus d equal to 0. Or ax0 plus by0 plus cz0 equal to negative d. So if you substitute that over here as negative d, so we have a projection n dot b over length of n, which is the component of b over n. So the distance, that's what I'm looking at, which is component of b onto n, absolute value of that, is from here, it's ax plus by plus cz. But here, instead of xyz, we should have written ax1, by1, cz1, because here we see x1, y1, and z1. Okay? So it is going to be ax1, by1, cz1, and here minus of minus d from this step, minus of minus d, that will be positive d, divided by length of the vector n, which is a square plus b square plus c square. So distance of the point from the plane, distance of the point x1, y1, z1, or distance of the point p1 from the plane is given by, I'm going to fill in this information now, it's a x1 plus b y1 plus c z1 plus d, absolute value of that, divided by square root of a square plus b square plus c square. Okay. So we have a problem. This problem is also worked out in my YouTube video for this section 12.5. So that completes the section. So I encourage you to look at these problems in the additional suggested problems of the exercise. And some of them are done in my YouTube videos for this section. Please check them out and watch for my next video for the next section.